And last time I talked about empirical formulas, mass percent composition. I introduced, or I refreshed your memories as to how, for instance, the coefficients in a balanced chemical equation are just conversion factors. How the molar mass is a conversion factor. How Avogadro's number is a conversion factor. Talked about how the formula of a compound gives you a conversion factor. So what I'm going to do here, okay, is I'm going to go through with you calculation of the molecular formula given a mass percent composition and the molecular mass. If you look back in your notes, you'll see that I gave you two different ways to calculate the molecular formula from this kind of information. One was the same thing that we did last week, which is first calculate the empirical formula. And remember, the procedure for that is change percent to grams, grams to moles, divide by the smallest, and so on. Once you have the empirical formula, then what you do is you calculate the molar mass of the empirical formula, and you divide it into the molecular mass. This is in your notes, right? And then once you do that, you round to the nearest whole number, multiply that whole number by each subscript in the formula, the empirical formula, and that gives you the molecular formula. And we did an example doing exactly that last Wednesday. What I'm going to do now is show you the other way, where we're going to go from the percent composition and use the molecular mass to calculate the molecular formula. Before I do that, remember there's an exam a week from Wednesday, right? Chapters 8, 9, 10, and 11. The experiment that we're doing this week, experiment 21B and 22, doing both of those, right? If you guys were in the first discussion section today, I told you that you're going to work with a partner on experiment 21B, but you're going to work individually on 22. I think we're going to have to work individually on everything. So, and I have right now I have it on my website that you're working with a partner in 21B, but I'm going to change that. So, you just need to know that you're going to work individually for the whole thing. Okay. So, back to this. So the procedure is going to be, we're going to from the percent composition, we're going to calculate how many grams of carbon in 1 mole of the compound, how many grams of hydrogen in 1 mole of the compound. And to do those, we're just going to convert these to the decimal, move the decimal 2 places to the left, right? And then multiply by the molar mass. Does that step make sense to you guys? If this was 50% carbon, then half of this mass would be carbon in 1 mole of the compound. Once we know how many grams of each element we have in 1 mole of the compound, we just convert those grams into moles. And so now we know how many moles of carbon we have in 1 mole of the compound, how many moles of hydrogen in 1 mole of the compound. That's going to be the molecular formula, just like that. So, this is using the percent composition as a conversion factor, basically. Now we know how many grams of carbon in 1 mole of the compound, how many grams of hydrogen in 1 mole of the compound. We're going to convert the grams of carbon to moles, grams of hydrogen to moles, using the molar mass of elements. So now, no matter what, at this point, you just round off to the nearest whole number. You should be really close to a whole number, as we are when we're very close. And this just gives us directly the molecular formula. It's going to be C5H10. That make sense? Okay, so that's how you do it the second way. It's up to you which way you do it. You should get the same answer. I think this probably is like 1 or 2 steps shorter. Who is it? This morning somebody mentioned to me that in sapling they use a different molecular orbital energy level diagram for a heteronuclear diatomic than I told you to use. Who is that? You're not here, whoever it was. Anybody remember saying that to me this morning?
I just said out of the book that
right?
Yeah, I guess so. Yeah, for the homework problem, you said lithium through nitrogen to use one of them, and the rest was oxygen, fluorine, and yeah, that's right. I guess NO was one of them, and I wasn't too sure which one to use. And they said use the lithium to nitrogen one for that one.
Okay, the book did that.
Yeah.
Okay, so do you remember what problem that is?
I have no idea.
Apparently one of the problems in the textbook tells you to, for nitrogen monoxide, it tells you to use the molecular orbital energy level diagram for lithium through nitrogen. But the rule that I gave you and the rule that I'm going to ask you to use is if one or both of the elements is oxygen, fluorine, or neon, use the molecular orbital energy level diagram for oxygen, fluorine, and neon. So that means for nitrogen monoxide, you would use one for oxygen, fluorine, and neon. Apparently the book tells you the opposite. Okay? Okay, do it that way. Thanks. Next, another problem, example. So what we're doing here is we're going to use an empirical formula to figure out basically the atomic mass of an unknown metal. Do you understand the notation here? So you know, you make a metal sulfide. You know the empirical formula is this. There's 2 metal atoms for every 3 sulfur atoms. You just don't know what the metal is yet. And do an experiment. You take 5.199 grams of this unknown metal, react it with enough sulfur, excess sulfur, and you get this many grams of the product, the metal sulfide. So we want to figure out what the metal is. The way that we're going to figure out what the metal is we're going to calculate its atomic mass, and look on the periodic table and see which metal has the closest atomic mass to that. That makes sense? So, how do you think we're going to be able to figure out the atomic mass or the molar mass of that metal from this information? Look at that for a second.
Now find out how much of the metal has reacted with the metal sulfide.
So we'll assume all 5.199 grams of the metal reacted.
How much sulfur was there?
That's right. Okay, so that's definitely what we're going to have to do. So what Rahul said was that we're going to take the difference between the total mass of the compound we make, the 7.377 grams, and the mass of the metal that reacted. The difference between those 2 numbers is the mass of the sulfur that's in the compound, right? Good. What now?
100%.
What's that?
Find the mass percent.
I'm not sure why we'd want to do that. I'm thinking something different. You might be able to find a path that way.
Use the molar mass of sulfur to find the moles of. Oh wait.
Yeah, that's right.
Yeah, to
Josh.
find the moles of that.
I was like,
You were going to say that?
I was afraid of being on water.
we all are, right? So what Josh said, and I like it, is use the molar mass of sulfur. Once we know how many grams of sulfur, use the molar mass of sulfur to figure out how many moles of sulfur are in our compound, right? What now? That's the second step. Where are we going, right? Are you just kind of blindly doing things that you can do, or do you have a...
If you divide that by the total, won't that give you the mass percent?
The moles would be the mole percent.
Yeah.
But we could get the mass percent. I think you can probably figure out a way to do this using mass percent. I'm trying to see if you guys can follow a different path. So we know
Mole to mole.
moles of sulfur. What do we want? Okay, but ultimately, what do we want?
Grams.
The atomic mass of the metal, and the atomic mass is the grams per mole, right? Which means, you see, we need basically 2 pieces of information to calculate that: the grams of the metal and the moles of the metal. You already know how many grams you have, right? And so where you guys got us to was moles of sulfur. Can you get to moles of the metal from there?
Yeah.
Because if you can, then you have everything you need, right?
Just use the empirical formula.
Use the empirical formula, Josh says, right? You guys see how that's going to work? So again, we figured out how many moles of sulfur we have in that compound, that much of the compound.
Then you multiply it.
That's right. When we have the empirical formula, we know there's 2 moles of metal for every 3 moles of sulfur. You guys see that? That's one of those conversion factors that I mentioned last time from the formula. See that? So now we'll know how many moles of metal we have in that much compound. We know how many grams of metal, 5.199 grams. Divide the 2, that's the molar mass. Look in the periodic table, see the metal, find the metal closest to that. See if it makes sense, right? It better be a metal. If it's not a metal, then some trouble. All right, so let's do all that. Right, subtract, right? All right, so we figured out how many grams of sulfur in that much compound, moles of sulfur in that much compound, moles of metal in that much compound. Make sense? Everybody see where we got the 2 to 3?
Yeah.
It's from the.
From the empirical formula, right? Okay. So now all we have to do is take the mass of the metal, divided by the moles of the metal, that'll give us the atomic mass. Okay, you guys, any questions? So, you okay with that? So now we know the molar mass, the atomic mass. Go to the periodic table for metal in that range. It's like, closest one's indium. See the atomic number 49 right there. So it's 114.82, 114.8, really close, right? So that means that the unknown metal is indium. That's a real easy one to ask on a multiple choice exam.
Yeah.
Transition back. I mean, I'm stupid. I think it's poor right now anyway.
I know, I
Maybe. Yeah. OB. Yeah. Gallagher. Yeah. It's probably some reggae band that's probably playing there too. Yeah. Close to the beach. Oh yeah. Yep. San Diego Bay right there.
This is a way that we have of figuring out, an experimental technique that we have of figuring out what the empirical formula of a compound is, typically hydrocarbons, but you can do other ones. It's called combustion analysis. And first of all, I'll show you how to do the calculations in a moment, but the way that the method works is you weigh out some amount of the unknown compound. You don't know what this compound is. You're trying to figure out its empirical formula. You weigh out, carefully as you can, that much. You put it in a combustion chamber. You're going to burn it, right? So you pump that chamber full of oxygen, you ignite it, and you burn it. You have a stream of inert gas that's going to go through there and push all the products out. Now, if it's a hydrocarbon, that member contains carbon, hydrogen, and maybe oxygen, then the products, you ensure it's complete combustion by really having a high pressure of oxygen in there and high temperatures. The products will be carbon dioxide and water. So what you do is you have a stream of inert gas that's going to push those products out of the combustion chamber and into a trap. You have a series of traps. The first trap is going to trap all of the water. All the water that was formed gets trapped in this one chamber, right? But the carbon dioxide doesn't. It goes through. It gets trapped in a second trap. The thing is, before you started the experiment, you weighed both of those traps. So you know how much they weighed to begin with. Then after you finished, you're going to weigh them again. The difference in mass is going to be, from the first trap, how many grams of water which were produced in this reaction. The second trap, the difference in mass, the increase in mass, will be the mass of carbon dioxide that was produced in the combustion reaction. The thing is, in general, this is just carbon and hydrogen. You know that because the only place carbon comes from is the hydrocarbon, and the only place it ends up is in carbon dioxide. You know that however many moles of carbon you have in this compound, that's how many moles of carbon dioxide you produce, right? Make sense? So, we'll do an example with this, but the idea is, because you know from the increase in mass of that second trap, how many grams of carbon dioxide were produced, you know how many moles of carbon dioxide were produced. Just divide by the molar mass. If you know how many moles of carbon dioxide, you know X, which means you know in that much of the compound how many moles of carbon there were. For hydrogen, because the only place hydrogen is coming from is the hydrocarbon, and the only place it's going is into water, because you put two hydrogens in one molecule of water, you know that, you know that however many moles of water that you end up with, you have twice that many moles of hydrogen in the compound. Does that make sense too? You know, get the halves and the doubles, you know, straight. But so what you do is you look at the increase in mass of the trap that traps the water. That's the grams of water that were produced. Convert that to moles using the molar mass of water. Multiply that by 2, because there's 2 moles of hydrogen in 1 mole of water. That gives you how many moles of hydrogen there were in the original amount of the compound. Okay? So now you know moles of carbon, moles of hydrogen, divide by the smallest, just like we were doing before. If it's 0.1 or more away from a whole number, multiply to get it to be within 0.1 of a whole number. If there's oxygen in here, then what you're going to do is, once you know how many moles of carbon you have in the compound and how many moles of hydrogen, you can convert those to moles, grams of carbon and grams of hydrogen using the molar masses. If you add those two numbers up, grams of carbon in the compound, grams of hydrogen in the compound. If that adds up to be less than the total mass of the compound you weighed out, then you know there was something else in there. If you know, and you'll be told this in these problems, that it can only potentially contain carbon, hydrogen, and oxygen, then you know the other element's going to have to be oxygen. Once you know that the other element is oxygen, all you do is take the total mass of carbon and hydrogen, subtract it out of the total mass of the compound. The difference is the mass of the oxygen. Use the grams of oxygen, convert to moles of oxygen. Now you know moles of carbon, moles of hydrogen, moles of oxygen, just like before, divide by the smallest, etc. Is that kind of okay? Kind of see that? So here's the procedure. You guys understand what I'm trying to say in the parentheses here? It might not be oxygen, it might be nitrogen or sulfur or something, but you have to be given that information. And if you know that, then you can, it works out the same way. You can still do that. So that's the procedure. Let's use an example. Illustrate it. So can I erase the procedure now? Does everybody have that?
Yeah.
All right, so first thing we did is we converted grams of carbon dioxide to moles using the molar mass. Converted to moles of carbon, and we're going to need this number, so I wrote this down. But we also want to know how many grams of carbon we have because we want to check and see if there's any oxygen. If you're told just that it's a hydrocarbon, like I did here, then it may or may not contain oxygen. Right? So you shouldn't assume that it doesn't or that it does. Just the way you check is you add up the mass of carbon, hydrogen. Any difference is the mass of oxygen is due to oxygen. If it's an element other than oxygen, as I said, you'll be told that. So next one. So we took the mass of the water that we tracked, converted it to moles using the molar mass, then converted that to moles of hydrogen, 2 moles of hydrogen, 1 mole of water. We save that number because we're going to need it, and then we multiply it times the molar mass of hydrogen to get the grams of hydrogen. Now what we're going to do, and you should always do this, is add up the mass of carbon and the mass of hydrogen, see if it's the same as the mass of the compound. This is 1 gram. If it's less and you're not told otherwise, then you should assume that there's oxygen in there. When we add these up, we get basically 1 gram, which is how much of the compound we started with. So we know there's no other element in there, just carbon and hydrogen. Okay, so now we can go back, take the moles of carbon and hydrogen, the smallest. They look like they're the same, right? So that's actually. So when we divide them, we get 1. So the empirical formula is CH, carbon and hydrogen. you have to be given more information. You need to know what the molecular mass is. If you did, then you can figure out what the molecular formula is. This could be acetylene, C2H2, well, but it's a solid, so probably not. It could be benzene. There's thousands of different compounds it could be. Any questions on that? So that's combustion analysis. That tends to show up on the exam fairly often. Make sure you do that. It ends up that you don't always need to know a balanced chemical equation to calculate everything that you can calculate. If you can follow just one atom, one element, if you know in the original compound, how many atoms of a given element there are, and in the product, how many atoms of that element there are, then you know the only conversion factor, the only ratio that you need to know. It's best just to illustrate this as an example. it down and then think about it. All right, so the idea here is that this compound, 3'-methylphenolic acid, fruit set, when it's ingested, it reacts with water in the body and produces several hydrocarbons as well as this compound metatoluidine. And metatoluidine is really nasty stuff. It messes with your kidneys and your liver and all this. But we want to know how many grams of fruit set you have to ingest to produce this many grams of metatoluidine. Now, the thing is that because there are several different reactions, we don't know what the balanced chemical equation is. There's several of them. We don't know. Well, you don't know. But the thing is, because the only thing, everything else that's produced is just hydrocarbons. There's no nitrogen in them, just carbon, hydrogen, maybe oxygen. The only place nitrogen goes is into the metatoluidine. So if we know how many atoms of nitrogen there are in one molecule of fruit set, then we know the ratio we need between fruit set and metatoluidine, because you're given the formula for metatoluidine, and you know there's one atom of nitrogen in every one molecule of that. So if there's one atom of nitrogen in fruit set per molecule, then we know it's a 1-to-1 ratio. And that's all we need. If there's 2, then it's 2-to-1, and so on. So the point of this exercise is that, this example, is to show you how you can do calculations like this without knowing necessarily what the balanced chemical equation is. So, all right, so given that, how do you think we're going to approach this? This is the question, right? How many grams of fruit set produce that many grams of metatoluidine? So what we need is we need a mole-to-mole ratio, right, between metatoluidine and fruit set. We can get that. We know the grams of metatoluidine. We can convert that to moles. If we have that mole-to-mole ratio, that's going to be the connection. Then we can get moles of fruit set. Right? If we know moles of fruit set, then we can get grams of fruit set.
We have to calculate the molecular weight of the metatiol.
Yeah, this one.
You have to do that still.
Absolutely. And why
That's
do
at
we
the
do
end,
that?
right? I was just, because
Yes, that's it.
you need to know how many moles there are per
Right,
gram.
so we find the molar mass, take the grams of the molar mass. That gives us moles of metatoluidine. But then we're stuck, right? Because we need to know the mole-to-mole ratio between metatoluidine and the fruit set. So how are we going to get that? We know half of it. We know there's one nitrogen per metatoluidine. Hey, how are we going to get how many nitrogens there are in fruit set? Yeah, we're going to need to know the molecular formula, right? And that's something that we've already done. We did an example at the beginning of class today. We did an example last week. I gave you mass percent composition. I gave you the molecular weight, right? You can use these. We will use these to find the molecular formula. And once we know that, then we'll know how many nitrogens there are. Okay, so we got to that point. So we figured out how many moles of metatoluidine. Now from the molecular formula of fruit set, we can get the mole ratio. That'll get us moles of fruit set, right? And then from there, it's a simple matter of multiplying times the molar mass molecular weight to get the grams of fruit set. Make sense? Let's do it. Let's do the let's get the molecular formula first. Okay. think, because I think it's a little bit shorter, I'm gonna do it the way I showed you guys just earlier today. I'm gonna take the percentage, multiply it by the molecular weight of solid. so you can see that the empirical formula, the molecular formula is C15, H13, NO3. Now, I did this because I wanted to work out another molecular formula problem for you guys, so you can get it from your notes. But to do this particular problem, you see that we only really had to do this step right here. Because that tells you in 1 mole of the compound how many moles of nitrogen there are. Once we see that it's 1, that gives us the mole ratio that we need. So if you're on a test, unless I asked you specifically for the molecular formula, you don't really have to. You just have to do this thing. All right, so now that we know that, we know the mole-to-mole ratio between metatoluidine and fruit set. Because there's 1 nitrogen here, and there's 1 nitrogen in fruit set, it has to be a 1-to-1 mole ratio. If that makes sense to you guys? That's the point of really this whole thing.
So it's 1 gram?
Is that?
Is it 1 gram?
No, 1 mole.
One.
The mole-to-mole ratio is 1-to-1. So now that we know that, we can get rid of all this. You guys get this for the molar mass of metatoluidine? Anybody get it? Anybody try it? Nobody just, okay, then you have to trust me. Alright, so we figured out how many moles of metatoluidine. Whoops, this is fruit. And because from our calculation over here, we knew that there was 1 mole of fruit set produces 1 mole of metatoluidine. We know how many moles of fruit set. We want the grams, so we're just going to take the molecular weight times the moles. And there's the answer. The last thing we have to talk about in this chapter is theoretical yield, percent yield, actual theoretical percent yield. If you had 142, then or 143, you've seen this, but I'm going to go over it again. Any questions on this problem before I go on? So, as you probably know, the theoretical yield is how much you calculate, how much product you calculate that could be produced in a given chemical reaction if everything goes perfectly, which, as you know from lab, never happens, right? And this number is always calculated. That's the point. You can only get the theoretical yield by calculating. The actual yield, that's how much you weigh at the end of the lab, and that's the amount of product that you actually got. So in these calculations, it's, in real life, you get that by weighing the product. In these problems, you'll always have to be given that number. And then percent, as you know, is actual over theoretical times over. Let's do that. So I give you a balanced chemical equation. I tell you how much reactants you have. I tell you how much product you make, and I ask for the percent yield. Right? So actual over theoretical times 100. What's the actual? Yeah, 2.19 is how much you actually get, right? So there's the actual yield. All we have to do is calculate the theoretical yield, divide, multiply by 100, we're done. So what should we do first to calculate the theoretical yield?
Find the limiting reactant?
Find the limiting reactant, and the reason you know that is because I gave you amounts of both reactants, right?
Yeah.
You have to figure which one's limiting, and use that to figure out how much product you can make, right? So remember the procedure that I showed you to find the limiting reactant, to change the grams to moles, and then divide by the coefficient. Do you remember that? So this is how you do it. It's real easy. All you have to do is find moles of all the reactants. If you divide by the coefficient of the reactants, with the moles by the coefficient, whichever of those divisions gives you the smallest number, that reactant's always going to be the limiting reactant. It always works out, no exceptions. So the thing to remember, the reason you always want to find the limiting reactant is that should always be the starting point for any calculations that you do. So let's apply that here. moles of each, then we're going to divide by their coefficients of the balanced equation. That nitrogen tetroxide, its coefficient is 1, so you can just leave this number as it is. Its coefficient is 2. So we're comparing this number and, well, this number divided by 1, which is this number. Of the two, this is smaller, a little bit, but smaller. So that's the limiting reactant. Now all we have to do is figure out our theoretical yield, calculate our theoretical yield of nitrogen, take our actual and the theoretical times 100. So remember to use the moles of your limiting reactant as a starting point. There's 3 moles of nitrogen produced for every 1 mole of nitrogen tetroxide. And about 28 grams per mole. That's our theoretical yield. The yield is just actual. Theoretical. Questions? That's the end of chapter 11. That's everything through this, from chapter 8 through this, we have to examine. On Wednesday, though, I do need to start into chapter 12.